Professor, I think you're on mute.
Oops, I'm sorry, I was muted all this time. So welcome to our 10th lecture on ECE 576 Information Engineering. From today's lecture, we are moving to the second unit in this course, which is topics on inference. So the idea is that many real-world applications, they have some interpretation in terms of the data that we are looking at. So they basically require inference instead of simply measuring information content. So when I say real-world applications, I mean things like text data, things like images, videos. So all of these have some context, some interpretation to the data. So if it is text data, for example, articles, we want to understand what is the content of the article, what is the topic of the article, and things like that. So articles of text require understanding of its of the topics, or the content. And if it is an image or a video, we would like to understand, for example, the scene or what are the objects in it. Right, so we really want to infer context from the data. So to allow us to do that, we require totally different machinery, and this remaining part of the course is going to introduce you to some useful techniques and enabling frameworks that can allow you to do it. So it's not going to be a very detailed treatment, but at least we want to give you an overview of all the elements that that can enable you to deal with that type of data and applications. Another example here is natural language processing. Again, you are faced with streams of data, but that data means something. So there are connections between words and sentences. So if you have that type of data, you want to help machines understand how words are related. Okay, so the key idea or the bigger picture is the following. So what we are going to do is we will represent, as I said last lecture, we will try to represent the world as a collection of random variables. Okay, so the emphasis is on representation, which essentially means we would need some tools to represent things. And the most effective tools are graphs when it comes to representing different variables and also highlighting the relationships and interconnections between them. So we'll see in the next few minutes what such representations are. But these random variables that I'm talking about can either be observed variables, and I'll call them x1 all the way to xn, or they could be unobserved. And in this case, I'll just call them z1 to all the way to zm. And they will have some joint distribution, joint probability distribution. Written as a probability of x1, x2, all the way to xn, and also combined with z1, z2, all the way to zm. So whatever situation you are dealing with, you will try to represent the entire world into some observed variables and some unobserved variables, and you can write down their joint distribution that describes the entire world. Okay, so the whole idea is you have some random variables and you know their density, and that's it. So essentially you know the entire scene, at least in probabilistic terms. That's exactly what happens when you have a random variable and you know it's a density function. So you know how much randomness is there and which values are more likely, which are less likely. So that's the information you need. Now to describe these probability distributions in a representation, we can make use of graphs. So I will say two of them are really unique and widely used. So compactly describe the random variables and their relationships we will use two type of models. So one is the directed graphical models. Okay, where you have directed graphs to represent relationships between random variables, and that happens when when you clearly know what causes what. Then you can use directed graphs to represent their relationships. And in common literature, basically these type of models are called Bayesian networks. So I'll highlight this. And you'll see why they're called Bayesian, because there's this Bayesian transition that is happening from one to the other. So it's clearly apparent that there is a directional flow of data, and you can capture that as a Bayesian update of the probability. So the second type of models are, as you can guess, undirected. Graphical models. And they are referred to as Markov random fields. Okay, so anytime you hear an MRF or a Markov random field, it's basically a undirected graphical model that is used to represent a set of random variables. Okay, so first idea is to represent the world, and the second follow-up idea is to learn or estimate the distribution from data. Okay, so first idea is you already represented it, but then you will need to know what are the probabilities or the conditional probabilities, because you are talking about Bayesian relationships. So second key thing is, can you learn or estimate the distributions from data? Okay, so if you have many examples or historical data, can you actually go and estimate the distributions from it? And in this aspect, again, there are several techniques used in the literature, but we are going to only look at one of them, and that's referred to as maximum, actually two. So maximum likelihood estimation, also called the MLE. And the other one is maximum a posteriori estimation, and that's called the MAP. So we'll maybe in the next lecture we will look at some estimation techniques. And the final thing is, once you have the representation and you know the probabilities, can you actually perform inference? And to compute the posterior distribution. That means using the example that we had, can you compute probability Z given x1, x2, and xn, or let's say they have values. So x1 already has the value small x1, x2 has the value small x2, and finally xn has the value small xn. So if you have some observations can you do some inference about the unobserved part of the world? And that's the whole idea of inference. Okay, so we'll take an example and then introduce some of the graphical models. So let's use a medical example or medical diagnosis example to motivate us on why these graphical models may be useful. So now we are in the medical diagnosis world. So we have a set of random variables, and some variables correspond to symptoms. So variable for each symptom, and let's say there are so many symptoms. For example, somebody can have fever, somebody can have cough, right? And these are all random variables in the world of medical diagnosis. But they have some relationships, we'll see, and we need some graph to help us illustrate those relationships. Or for example, fast breathing, right? And shaking, nausea, vomiting, and so on. So there's so many symptom variables. Let's highlight them. And we can also have a variable for each disease. And again, there's hosts of diseases, and in a good database you can have lots and lots of these symptoms and diseases. So for example, in this toy example, we will have pneumonia, we'll have flu, common cold, bronchitis, tuberculosis, and so on. Okay, now if we have this world where these are the variables, basically the diagnosis is actually a inference over in this model. So the diagnosis is actually an inference question. Diagnosis is performed by inference in the model. So when I say inference, basically I'm looking at some observed values and some unobserved values, and I want to have I want to ask a question, and that question can be, for example, what is the probability that pneumonia is 1 given cough is 1, fever is 1, vomiting is 0. right? So hopefully that's the kind of thinking going on in your mind when you're trying to do diagnosis. So if you have a set of you have an observation set, and based on those observations, you want to ask yourself a question. And again, this is a huge world, so you will have many, many different symptoms that we are not putting in here, but essentially the whole idea is conditioned on all their values. What is the probability that you have a certain underlying disease? So that's the inference question. And once you have the answer to this, you can reach a conclusion on your diagnosis. Now, I mean, just for your information, that there's a model out there, so that documents all these probabilities, and that's a model used by medical researchers. It's called Quick Medical Reference, or QMR DT. Okay, and it has about 600 diseases, disease variables, and 400 or 4,000 findings. Okay, so and that type of model is actually a graphical model. So for example, you will have some underlying diseases like pneumonia. You can also have tuberculosis, right? And you can have a host or bunch of other diseases under or in this model, right? So there's 600 of them, and each disease can be represented as a circle or a node. And then you have symptoms, so you can have, again, nodes for your symptoms. I'm just putting up quickly some of them. Fast breathing, shaking, nausea, vomiting. Okay, so these are all the symptoms. Now, the relationship between diseases and symptoms are directed links. So if you have pneumonia, you may have, I mean, this is just hypothetical example, you may have fever. This causes cough. This may also cause shaking, right? It may cause vomiting. Oops. Similarly, if you have tuberculosis, you may have fast breathing, you may have shaking, you may have vomiting, right? And so on and so forth. So you have a model that comes from your underlying knowledge of how diseases and symptoms are linked. But then you want to understand the probabilities of certain these links, and that helps you ask reverse questions. So obviously, you may already know that if you have pneumonia, with a certain probability, it has a fever. With a certain probability, it will have cough. These can be obtained from experimental or historical data. But when you want to ask the reverse question, that means what is the probability somebody has a certain disease given a certain symptoms are active? Now, that probability is a reverse probability. So then we need inference, and inference basically would mean you want to compute that probability, and that probability can actually be computed by joint probabilities and their using those to compute the conditional probability. So I can give you an example here. So for example, if all these random variables were independent, then their joint probability is just the product of all the probabilities. But then you don't have any structure. So when you have these links, you will have some structure in your joint probability distribution. So let's write down what is going to be the joint probability if you have a simple model. So what I'm trying to say is, if you want to find probability A given B, you actually do the joint probability over the marginal, and that's where you get your A given B. So your inference question is exactly A given B, but there is more complexity to it. And hopefully, if your data can be represented as a graphical model, you can leverage that structure to simplify it and actually compute it. Because otherwise, if the number of variables are extremely large, then computing this may not be possible. Okay, now, so let's look at the structure. In through independence. Can everybody be muted if you're not speaking? Okay, so if we have a world with variables x1, x2, xn, which are independent, then, as you know from the earlier lectures, that the probability of x1, x2, x3 all the way to xn is actually the product. Right? Okay, so now this is not a very useful property to have. So this does not a useful property for inference, because observing a variable xi or xi does not influence our predictions. Right? Predictions, let's say, on xj. So in other words, if all these circles here were not connected to others, then that means that they are all independent. So knowing some variables and not knowing the others would not help you predict anything, because nobody is or no symptom or no disease is linked to any other disease or symptom. Now, if x1 to xn are conditionally independent, so there's this new term coming up called conditionally independent. So if x1 all the way to xn are conditionally independent, and when I say conditionally independent, that means given certain variables, you will be independent. So conditionally independent given y, so denoted as, so if when I want to say this, I will say, or I will write xi is conditionally independent of x minus I given y. So minus I means the shorthand for everything except I. So, for example, if our model was the following, where y is here and our x, this is x1, this is x2. If our model is has this structure where y leads to all the x's, then then basically you can write your joint distribution as follows. So your probability of y x1 xn is actually equals to probability of y times probability of x1 given y times the product of I2 to n probability of xi given x1 xi minus 1 and y. Okay, so this is complicated to understand. So maybe I can write you a chain rule of conditional probabilities. So let's write down an anecdote here. Or let's say an appendix. So chain rule for joint probability distributions. So for example, if you have probability of A and B, that you can write down as probability of A given B times probability of B, right? Everybody has seen that. Okay, so if you have three variables, A, B, and C, you can prove that this can be written as probability of A given B and C times probability of B and C, okay? But the probability of B and C can again be written as a different probability. So this is A given B and C, and this is B given C, and then probability of C. Okay, so essentially, if you look at the pattern, and you can actually prove it for larger sequences. So if you have A1, A2, all the way to AN, you can write it as probability A1 given A2 all the way to AN, okay, times probability A2 given A3 all the way to AN, times so on. And the last term will be probability AN minus 1 given AN and times AN, or the probability of AN. Okay, so that's the chain rule. So you take the first variable and condition on all of the others. And you take the second one, condition on the others which are larger than that one, 3 onwards. Then you take A4 and you take A5 onwards as a condition, all the way up till the last one is picked. So this was just a additional information here. So when I try to write down the joint probability between y and x1 to xn, basically I can pick y first, and then so this is written in a reverse order. So y is the last one to be picked, and then x1 given y, and so it's like this one. So it's an is playing the role of y. But if you write this and your structure is the graph shown on the left, you can actually show that this is going to be probability of y times probability of x1 given y times the product probability of xi given y. And this is the reason is because xi is conditionally independent of x minus I given y. So if this holds, then you can see that the joint distribution can actually be written as the probability of y times probability of x1 given y times x2 given y, x3 given y, and so on. So I'm going to write down a general representation for that, but in this simple example, you can see that the structure can help you write down the joint distribution in a certain way. Okay. Now I'll formalize this now. So if you can exploit structure to write down joint distribution, then we can look at it. Structured networks or directed graphical models called Bayesian networks. Now, a Bayesian network formally is defined as a directed is specified directed acyclic graph G equals to V and E, where V is the set of nodes and E is the edges, right? So we want to have a node, so one node I belongs to V for each random variable. Every random variable will have a node in the Bayesian network. The second thing is we will have one conditional probability distribution. Or you can say CPD per node. And you can also write it as the probability of xi given x parents of I. Okay, so this specifies the variables probability distribution conditioned on its parents' values. Okay, now this Bayesian network, we can have a certain form of the joint probability distribution. So in a Bayesian network, so this thing is very important. This is actually the most useful property why Bayesian networks are used. The joint probability distribution can be factorized as follows. So you have the joint probability x1, x2, all the way to xn can actually be written as simply the product of I over all the nodes of the probability xi given x parents of I. Okay, so I will say this is the most critical advantage of a Bayesian network, that if you have a Bayesian network, meaning you have a directed graph to represent your world of random variables, you can actually find the joint distribution in a very compact way. So you don't have to look at all the variables separately, or you don't have to write the whole chain rule for it. You can just write it in a product of conditional probability distribution. So if you will, this thing here is called a this is a CPD, conditional probability distribution. Okay. In other words, this is what I'm referring to. Now, I mean, this is a powerful and useful model. So it's a powerful framework for designing algorithms to perform probability computations. And it enables use of prior knowledge to specify a part of the model structure. Okay, so let's consider an example where you see how a Bayesian network comes into action and how we can actually compute the joint probability distribution. So I have a picture to help me provide that example here. Let's use this. Okay, so let's use this example. So this example says that there is a Bayesian network representing the grade you will get in the course, or the letter grade that you will get in the course. No, it's the so there's a context to this example, which is that there's a bunch of random variables. For example, your grade on a particular test will depend on whether the exam is difficult and whether you are intelligent or not. So there's, let's say, two variables representing your course grade. Similarly, if you're intelligent, you may also have a SAT score which reflects your intelligence. That's great. And if you have a certain grade, then whether a letter will be sent to your parents or not also has a certain probability. So for example, if you have a grade G1, then there's a very high probability that a letter will be sent, and so on. So the meaning of this whole picture is not very important. I think The key idea is that, let's say you have a certain scenario which can be represented as a collection of random variables. Obviously, something being difficult is a random thing. Whether somebody is intelligent or not is a random thing. Again, grade is random, but it depends on underlying factors. Similarly, SAT scores are probabilistic, but they have some dependence on intelligence and so on. So this is the Bayesian network that we are dealing with. And each variable represents a node, which is great. And you have edges there. Again, that's great. But now important thing is that you have, for every node, you have a conditional probability distribution, or CPD. Okay, so let's put this here and say that each of this, so each of these tables are, so it's a CPD, which says what is the probability of G given I and D, right? So it's a probability of that node given its parents. So parents here are difficulty and intelligence. So if you want to describe this random variable, you actually need a CPD for it. And CPD is in this form. It's like a table where the conditions are here. And these are the probabilities for each outcome. So in this case, you can have 3 values of grades, G1, G2, G3, but their values depend on whether intelligence is 0 and difficulty is 0. Intelligence is 0, difficulty is 1. Intelligence 0, difficulty 0. Actually, this should have been a, no, this is correct. No, I think there is a mistake here. So this should be a 1, and then this should be a 1 here. Yeah, so all possible values of the conditioned variables and all possible outcomes, so we can have a probability table. Again, this is the CPD that corresponds to the probability of SAT score, or S, given I. Okay, and again, the others are also CPDs. So if I ask you to write down the joint distribution of this Bayesian network, what I'm asking you to write is basically the joint distribution of all the random variables, which is this thing here. And I've just told you that if you have a Bayesian network, you can actually write down the probability joint distribution as the product of all the CPDs. So CPDs are probabilities of the variable conditioned on its parents. So if a variable doesn't have a parent, like the difficulty variable here, we just put the difficulty variable as it is. So that's the first CPD, which is probability of difficulty. Then probability of intelligence. Because they have no parents, so we just write them out as it is. But when it comes to grade, it has 2 parents, which is intelligence and difficulty. So we have to write it as the full CPD, G given I and D. The next one is SAT scores. So S is conditioned on I. And finally, the letter is L given G. So that's all. I mean, if you want to find the joint probability, it's just the product of all the conditional probability distributions defined by the Bayesian graph. Otherwise, you would have to write the chain rule, which is the following. So for example, if I have no structure, what I will say is, all of this will be probability of D given I, G, S, L, then probability of I given G, S, L times probability of G given S and L times the probability of S given L, and then probability of L, something like this. But again, this one has the added difficulty of computing these probabilities because we don't know. But in a Bayesian network, there is a structure. So, I mean, in this case, look, if you were to find the probability of L, that would be very complicated because it depends on all the other variables. So the factorization in a Bayesian network actually helps you write those factors out explicitly and makes it very easy to compute the joint distribution. So we'll see more examples here. And one classical example where Bayesian networks are actually very helpful is in diagnosis or asking questions in practical applications. So for example, if you were to ask yourself an automotive related question of whether your car will start in the morning or not, this is an example Bayesian network that can help you answer that question. It's actually taken from a paper, but automotive companies come up with these graphs to understand how reliable things are and what is the possibility of something breaking down. But I mean, if you look at this example, it's very interesting relationships between different variables. For example, if you want to see whether start is 0 or 1, it depends on many things, whether the distributor is working, whether the fuel pump is working, spark plugs are okay, and with all of these, whether the engine cranks or not. And if the engine were to crank, the starter should be okay, the leaks too should be okay, battery should be there. For the battery to be there, battery is actually powering radio, it's powering lights, it's powering other things here. For the battery to be okay, you need to have charge on it. And the charge, again, depends on the alternator and the fan belt and things like that. So this is like a map of the system. and doing inference on this is actually finding out conditional probabilities. So for you can have questions like, what is the probability the car starts given that the radio is on, right? Obviously, that's a possible question. So if you want to do that, then finding the joint probability is actually made simpler by exploiting the structure. So I can give you an example here. So if you have all these variables and you want to find the probability start equal to 1 given so many other variables, and the radio equals to 1, and so many others. Okay, so this is actually the joint probability divided by the so I can say this is the probability Okay, and divided by the probabilities of all those. Radio equals to 1 and all the others. And these joint probabilities can actually be computed using the CPDs. Okay, and CPDs come from data, they come from experience, they come from historical information. So once you have that information, I think you can compute this and start to give answers to questions. Hopefully in the next homework, you will see a software tool that can also help you to visualize things and come up with numbers. Again, it's hard to write everything down here, but softwares can actually be programmed to give you answers. So homework 5, I guess, will have a link to a tool that can help you visualize these things. Okay, next up is an example on the use of Bayesian networks in generative models. So when we talk about Bayesian networks, in some way they are generative models. So when I say generative model, I mean it's the way data is generated. So for example, I'm not sure if you've seen this in a machine learning class or some other class. A very basic model of in machine learning is called a naive Bayes classifier. Okay, so it's machine learning 101. First lecture, you will see a classification model, and that's called a naive Bayes classifier. So that model is a model where I mean, if you take their basic example of sorting out or filtering emails into spam and ham, what they tell you is, there is a variable y, right, that captures spam and ham. There are labels, spam and ham, and then you have features, right? So x1, x2, so many features. So if a email is spam, it will have all these features with certain probabilities. So for example, the number of dollar symbols in an email, right? Or, number of lottery mentions. So these are all features, and the classifier is whether a email is a spam or a ham, and that's why. So this model looks like a generative model. In other words, if you want to generate a spam email, this is what you need to do. I mean, that email should have these features with certain probabilities, right? So inference generally deals with the reverse question saying, if these are observed, you observed X1 number of dollar symbols, X2 number of lottery mentions, and X3 and X4 features, then what is the probability that it is spam or it is ham, right? But if you were to do the forward thing, you will actually generate an email. So essentially the idea is, can you learn a generative model of the event or the process? Okay, so we can interpret Bayesian network as a generative process, right? So for example, to generate an email, we decide whether it is spam or not spam by sampling y from a probability of over the variable y. Okay, and then for each word, I is 1 to n, sample xi from a probability distribution of x I given y equals to y, right? And by the way, I forgot to mention that a naive Bayes classifier is called naive because of the naive assumption that all the features are independent, right? So it's a classifier, but the underlying assumption is actually, sorry, the underlying assumption is that all the data samples are independent. Okay, so I take my words back on the features, but it's all the data points or samples that we use to learn the model are independent, or IID. So that's the naive assumption, and that's why we call it naive Bayes classifier. But anyway, the point I want to make here is that Bayesian networks can be used to represent such generative models, and you can use machine learning techniques to actually learn this model. Okay, so classification is one example. If you learn a classifier, you're actually learning this CPDs, or you're learning the Bayesian network. Okay, now some properties that come along with the structure of Bayesian networks or Markov random fields. We haven't seen Markov random fields today, but next lecture we are going to look at those. Those are a little more messier than this, but again, they are also very powerful and very widely used in machine learning and all this information sciences. Okay, now what are the conditional independencies that we can see from the Bayesian network? So maybe I can say that the Bayesian networks implies conditional independencies. Okay, so what do I mean by that? So let's take an example of the same Bayesian network that we had earlier. So we had a difficulty variable intelligence and then we had a grade. So this is linked to this, and we had an SAT, and then we had a letter. And we said the joint distribution for this can be easily written so the probability DIGSL can be written as the probability of the node given its parents for all of them, and you multiply them together. So we start with the difficulty. So D does not have any parents, so it's just P of D, then P of I, and then P of G given D and I. Then we had P of S given I, then P of L given G, right? And that's it. That's your, so as I mentioned before, by chain rule, you could have written it as follows. You could have written it as DIGSL equals P of D, P of I given D, P of G given I and D, P of S given I, D, G, and then P of L given G, D, I, S. Okay, so that's the chain rule. Now, if you look at our factorization, what we are saying is, P of I given D is actually just P of I. Right? If you just compare term by term, this term is this term. This term is just this term. So we are assuming, or we're not, we're just implying. So we are implying that P of I given D equals to P of I, right? So in other words, what we are saying is that D is independent of I, isn't it? Then in the second one, we are saying that P of S given I D G equals to P of S given I. So if you look at this, we are saying that S only depends on I. So S is independent of D and G given I. So S is independent of the two variables D and G given the variable I. Okay. And then we are saying probability L given G D I S is actually equals to L given G. So what we can say is that L is independent. The L is independent of the three variables I, D, and S given G, right? So these are conditional independence statements. Now, I mean, doing this every time and looking at the conditional independence is hard. So there are some rules that can allow you to just look at a graph and say what are the conditional independencies that are implied by a certain graph. So I have a picture to illustrate all of those. So let me bring that up here. So it says, generalizing the above arguments, we obtain that a variable is independent from its non-descendants given its parents. So for example, if you have a structure like this, you can say that given a parent, I mean, given B, A and C are independent, right? So you know that B causes A and B causes C, but let's say you've observed the value of B, then now A and C do not have any dependence anymore. Okay, so the first rule says fixing B decouples A and C. Now the second one is cascade. So if you have a cascade situation, then if you know B, then A and C become disconnected. So A and C are independent given B. The next one is the V structure. So if you have two variables that cause a third variable, and now you've observed C, then this actually decouples A and B. So these are three rules that you have to remember to simply look at a figure and say what are the conditional independencies. We will take example here, and also I'll give you an algorithm to determine that from a picture. But just to clarify why these rules apply, you can actually prove each of these three statements. But I can just give you a justification for one of them. So let's say you observe B. Now the statement says A and C are independent given B. So in other words, maybe I can say it here. Okay, statement A and B, A and C are conditionally independent given B. Okay, so the expression for this is, or let's say implication is that given B, so A, it's so if you know B, then A and C are independent. So then this is just A given B. Okay, does everybody understand this? So A and C are conditionally independent given B will actually mean that you are saying this. Now the proof is the following. So let's say you had this network and the joint distribution can be written as this, which is easy because you can look at the Bayesian network factorization. So you'll first have probability of B, then A given B, and then C given B. Okay, that's simple. So now what you write is probability A and C. Yeah, that's another way of writing it. So I mean, if I can say this is one way, or I can also say if A and C are independent given B, so this will be probability of A given B, C given B. Yeah. So if I can show this, both of them imply that that the independence is there. So in this example, if you start off with probability of A and C given B, you can write this as the joint divided by probability of B. The joint can be written as this factorization, and the probability of B and B cancels, so you were just left with this part, which proves that conditional independence statement holds. So I encourage you to also look at other examples here, the other two cases, and you will see that you can actually justify the statements. Okay, so
Professor, before you go on, I just have a quick question.
yeah,
I wanted to know, like, for this, are we actually going to be calculating specific problems, or are we just deriving, I guess, the proofs? What exactly are we looking to do with these, from these examples that you have showed us?
yeah. So the idea is not to I mean, not to put you into computational work on paper. I think you will be required to understand the concept. So for example, if I give you a graph, can you write down the factorization for joint probability? Like, for example, this is a very straightforward thing to ask. If this is the graph, what is the joint probability distribution? So obviously that's this thing here, right?
Okay. Yes.
Now, computing this is a different thing. Computers can do it. I think in this lecture, I don't expect you to do computational work. It's just using rules and getting the structure of the joint probability distribution. That's the whole trick. I mean, rest computers can do it. Algorithms are there. But just to explain you the idea how we are able to use those algorithms to learn these graphs. Okay, so I think in this lecture, I'm assuming you're asking for the quiz, we will just have a test of facts. So if I give you a diagram and I ask you whether A and C are conditionally independent given B, is it true or false? That's for you to figure out.
Okay, thank you.
Okay, yeah. Okay, yeah, so I think we are, we can take a few examples that can help you see how conditional independencies can be figured out. So let's take a look at an algorithm that, so D separation, which is an algorithm to determine conditional independencies. From a graph or a Bayesian network graph. Okay, again, I think it's, I will use a figure here to make it a little easier. Okay, now if you have a Bayesian network and you want to understand whether a certain conditional independence statement holds or not, then either you remember the three rules or there's a ball rolling algorithm. So, which is the following. So if you want to determine whether two variables are independent conditionally on a third variable, then this algorithm says that you just color the conditioned variable. So in this case, you colored the variable y, and now you can see that you can ask yourself, is x conditionally independent of z given y? So to determine this, I mean, if you condition on y, so that means you colored this node, and you try to roll a ball from x to z, and you will see that there's a roadblock. So there's a blocked path. Maybe I can just write it here as same thing from z. If I roll a ball from here to here, you experience a roadblock here. So so we can say that x and z are conditionally independent. Okay, but otherwise, if y was not observed, then x and z are linked. If you roll a ball from here to there, you can do it. Okay, and the same thing from this way. So in the influence of x is on z through y, and the influence of z is there on x through y. But if we conditioned them on y, then basically we decoupled them. Okay, so for example, if you had unobserved variable y, then an active path exists. Okay, so that means X and Z are coupled together. Okay, so this is for the case where you have a common root node, right? I mean, this is one type of scenario that you can encounter. There's another scenario where you have common parents. So that's a different case. And that actually has a reverse logic. So, okay, first maybe I can just say yes to this question. So is X and Z conditionally independent given Y? The answer is yes. Okay, because there is a blocked path from X to Z given Y is observed. Now look at the second scenario where you have common parents. Now this has a reverse logic. So if you have a common parents, then observing the child node actually creates an active path. So for example, in this case, is X independent of Z conditioned on Y? Well, the answer is no, because knowing Y creates an active path between X and Z. But on the other hand, if a Y is unobserved, then you have a blocked path. Okay, so this is very important to understand. I mean, these two are totally different. So here, when Y is unobserved, you do not have a path. Okay, but on the first example, when Y is unobserved, you have a path. Okay, so one way to remember is to see if the arrows are in opposite directions, then you cannot just simply create an active path. Okay, in this example, there was no arrows here, so you can actually connect them. Now, if you observe Y, then it's a different story. So observing Y in this case actually enables the path, so it actually gets rid of the blockage created by the arrows. But on the first example, having an observed Y actually creates that blockage link. Okay, so this was a simple rule. Now let's say let's take another case, which is a cascade scenario. So to see whether X is conditionally independent of Z given Y, we can look at the graph and see whether there is an active path or not. Now, if you observe Y in the middle, then there is a blockage or the path is blocked. Otherwise, the path is open. So there is a link between X and Z. and the same thing between Z and X. So knowing these three rules, I think you can easily find answers to conditional independence queries. Okay, and the reason why it is it's important to know these conditional independencies. It's because it allows us to quickly prune the Bayesian network and to find just the relevant variables for answering a query. So if I asked you what is the probability of x1 given given x2, x3, x100, you can quickly use a tree to find out the conditional independencies and tell me, hey, you know what, x1 only depends on, or is only, so if you conditioned on x2, that's enough. I mean, then that makes x1 conditionally independent of everything else. Okay, so if you have that type of information, then you can actually simplify your inference questions. So if I go back and give you the example of the car, starting example, if I ask you what is the conditional probability that the engine starts given that the engine cranks. So since the engine already cranked, I don't need to worry about whether battery power is there, whether it's charged or not, or leaking, and fan belt, and so on. Because it's already told me that it's conditionally independent. So if I observed this, that's it. I mean, I can cut this large graph to two pieces. I can just figure out the conditional probability of this link. Because knowing this, you're actually independent of everything which is here. So you see, the reason why we want to do this is it simplifies our inference question. So how to do this is using that deseparation algorithm, which has these three rules, which you have to remember, and we can do an example to, or maybe more than one examples to see how the algorithms can help you identify the independencies. So I'll give you an example and I'll ask you some questions now. So here is a example on a Bayesian network, which has two observed random variables, x2 and x3. And the question is x6 conditionally independent of x5? So we are looking at x6. Is it conditionally independent of x5 given x2 and x3? So now I need you to look at this graph, look at the algorithms to see, do we have an active path between x6 and x5 conditioned on x2 and x3? Okay, I need volunteers now. So I just need an answer to the question here. The question is whether this is true or false, and why do you say this? And that's the type of questions you should be expecting on the quiz. Okay, so I'll do the first one for you, and then maybe the next one I can ask for volunteers. So if you see X5 and X6, they are just connected to each other. So there you see that there is an active path here, right? So what you can say is that there's an active path which exists between X6 and X5, but let's see whether there are other paths or not. So if you look at the other path between X6 and X5, that's coming from here, right? So going here, 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 here. But is that active? Let's look at that. So you see that this link is like a cascade link, right? And if you've observed a variable in that cascade link, you actually have a blockage here, right? So this active path does not exist. And the same thing if you start from this side. So if you start from this side, you have a stop here. So you do not have an active path from X6 to X5 from this route. But you have obviously a direct route, so that's all that matters. So yes. So given X2 and X3, X6 is dependent on so it's not conditionally so you cannot say it is conditionally independent, right? So it's only conditionally independent if you can separate it, if you can kind of isolate it by some sort of a blockage. Now the next one, I need somebody to help me with that. So I'm looking at X4, which is here.
That will be conditionally independent. Because
So yes or
no? In X2.
Oh, sorry, it's X4 and X5, yeah?
Yes, it is conditionally.
Okay. Why do you say this?
Because that's the block on X2.
Yeah, so active path is actually blocked here.
Yes.
Right, so you're actually isolated. The moment you know X2, you cannot go here, you cannot go here, right?
Yeah.
So yes. So yes, they are
Conditionally independent.
Yeah. Okay, excellent. Now let's look at a more I mean the same example but little different queries which will test you on the other rules that exist for conditional independence. So let's look at this example. And the query is X4 conditionally independent of X5 given X1 and X6. So here's X4. Here's X5. Are they independent conditionally on X1 and X6? So I can tell you there is one route here. There is one route here. So you have to see whether there is a blockage somewhere or not. So I can already see that in this route, you are encountered by a block on the active path, right?
Yes,
Because the
but
source.
from the 6, I think, is that the reversal of the block?
Yes, so from 6, luckily,
We have a path.
yes. So
Does it resist?
yeah, so this path is open from here, and observing X6 actually couples them because you see there's 2 arrows coming towards X6. So when you observe it, it actually opens up. So this path is a legitimate path. So you will say yes, because an active path.
So this is a,
1 second. Okay.
they're not conditionally independent.
Yeah. So they are not, because there is an active path. And now we are at our last query. It's about X4, X5, simply conditioned on X1. So we have the same example, but we have unobserved X6.
Yes, so this will be, yes, conditionally independent.
Yes, so I mean, this path will be blocked, right? So we are left with the other path, which is also blocked. So the answer is yes. Okay. So if, I mean, in the same figure, we can ask many different queries, but it depends on the context. I mean, once you have an inference query, you can actually simplify your query with the help of a D-separation algorithm, and you will have more chances to do it in the quiz. Now, D-separation also implies some equivalence. So if two different Bayesian networks have the same conditional independence assertions, then we say that they are equivalent, because you can just rename the variables and they will become the same. So let's see if I have, yeah, I do. So to tell you if networks are equivalent or not, you can also look at the conditional independence assertions. So if any two networks have the same, then they will be the same networks. So again, I want your help now because we have 4 networks. And my question is, which ones are equivalent? So we have to look at, so let's see, for the first one, what are the conditional independence assertion? We can say, so is X independent of Y given Z? So if I just ask you, if is X independent of Y given Z? So let's look at one by one. So if in this case, if I know Z, does this make X and Y independent?
Yeah, if we don't have Z there, yeah.
Yes. So this is like a cascade network. So if you know Z, then X and Y become independent.
Yes.
Okay, very good. So in the second one, it's the same, right? So it's just like you replace X with Y and Y with X. So you rename them, the network is still the same. Perfect. Now, how about the third one? If you know Z here, does it decouple X and Y?
No.
No.
I think it does. So now there's a blockage here, right?
Yes, yes. If you, yeah.
So it's still an equivalent network. Now the fourth case is the critical
But
case.
Professor, isn't there there's still a path between X and Y though? Is it not?
Which one?
For C.
No, for C, you have to look at the direction of the arrows. I mean, arrows are this way, right? So if you want to look at a path, there exists a path here and here. So this is exactly the case we saw here in this example. So if you have a common source, then observing that source variable will create a blocked path. Is that clear?
Okay.
But it's not the other way around. If you have a common parent, so if one node has 2 parents, sorry, not common parents, it's different parents here, then I mean the arrows are this way. So now observing Y actually couples them. So this is the tricky part. So if you had a common source or one source for 2 different variables, then observing that variable actually blocks the path between X and Z. But in this case, observing the variable actually opens up the path. And this is exactly what I was about to say in the fourth example, where X and Y point towards Z. So now if you observe Z, then the path opens up and X and Y become dependent. So the answer is no here. And therefore we can say that A, B, and C are equivalent structures. Okay, now this was a very simple example because we have only one conditional independence statement. But if we had more complex networks or with a larger number of nodes, things will be different. So let's see if I have another example. I mean, this will also help you understand it better because we have more number of nodes. And we will obviously have more cases. So the question is, are these equivalent? Now, to look at this, I think you have to understand whether they imply the same conditional independencies or not. So in this case, what are the things that you can condition on? I mean, if you just had 3 nodes, you could condition on just the center node and see the independencies. But here, I think you can either condition on W, you can condition on X, condition on Y. Right, so 3 possibilities. Conditioning on V and Z doesn't matter because it's already at the edge, right? So it's already in the corner. So if we can prove that the conditional independencies given W, X, and Y are the same for both networks, then they are actually equivalent. So our question will be, is V independent of Z given W? Is V independent of Z given X? And this question is V given independent of Z given Y. Okay, so let's look at the first network. Now, if I condition on W, is there an active path or not?
No.
Yeah, so we don't have an active path because this was like a cascade link and you couldn't cross this point. So knowing W decouples it, so V becomes independent conditionally on W. Now, if I know X, the same thing happens, right? We have this path is open, but then we go and hit here. So again, it's independent.
Same thing for the other one.
No. So if you know Y, you see the arrows are both pointing towards Y. So the moment you observe Y, you actually open up the link. So this time,
Because the arrow is on the other way,
I mean, you're having different parents of Y.
Oh, okay.
So the moment you observe Y, you actually connect them together. Okay. So then V and Z are not independent.
If the arrow was the other way around, it would have been yes, right?
Yeah, if this arrow is here,
Okay.
then yes, you are right. Okay, for this, we have computed the independencies. Now look at the other network. So V and Z given W. So let's say W is known. Then, I mean, this was a cascade, but it got blocked here. So yes, they are conditionally independent. Now, if X is known, X is here a common source of W and Y, so knowing X actually blocks the path. So then again, V and Z are independent. And finally, if you observe Y here, you have the same problem. So the path becomes open. So this is open, this is open, this is open. So you are not independent conditionally anymore. So what you will say here is that both Bayesian networks are equivalent. The reason why I say it's equivalent is because your joint probability just depends on the product of the conditional probability distributions, CPDs. And if your independence statements are the same, then CPDs are the same. And that's it. Doesn't matter where the arrows are. It's going to give you the same inference results. Now, the last example is of a very commonly used graphical model. So that's called a hidden Markov model. The name is very complicated, but it's actually a very simple thing. That's also a Bayesian network. So hidden Markov model looks something like this picture here. And the reason why it's called Markov is because it depends only on the previous variable. So every node only has a dependence on its previous node. So it's like today just depends on how yesterday was, and tomorrow will depend on how today is. So it's one-step dependency, and it's attributed to Andrei Markov. Right. So whenever we say Markovian, Markov chain, Markov model, it's actually one-step dependency in the network. And the reason why we say hidden Markov, it's because there is some hidden states in this model. So for example, if you consider a communication example, let's say you transmitted Y and you received X. So let's say you have a sequence of bits, right? So bits are related. If you transmitted Y1, then the next bit has a next bit Y2 has a relationship with Y1, and the next one has a relationship with Y2, and so on. So you transmit a input sequence, and what you receive at the receiver is a sequence of X's. Now the question is, after observing X1, X2, X6, what is the probability that a certain sequence was sent? So that's the detection problem, right? So you see that a detection problem is also a inference problem, and it can be solved using the help of Bayesian networks. So if you can consider that your communication problem is or can be modeled as a hidden Markov model, which is a graph, then you can do inference using tools of Bayesian networks. Now, if this was the model, then your joint probability can actually be written as the following. So it can actually be written as probability y1 times probability of x1 given y1, x2 given y2, x3 given y3, x4 given y4, x5 given y5, x6 given y6, and y6 given y5, y5 given y4, y4 given y3, and so on. So all these links. So basically you can write them as a product of yt given yt minus 1 and xt given yt. So that's the joint distribution. And because it has this Markovian structure, the joint probability distribution is actually very compact. So if you look at this, y1 is the distribution for the starting state. Yt given yt minus 1 is the transition probability between any two states. And xt given yt is the emission probability. So all these components have a very relatable meaning. And in this, if you want to find the conditional independencies, it's also very simple, because the moment you know your parent node, then you're actually independent of everything else. But it's like a chain. So if you observe y6, then x6 is independent conditionally with everything else. So y6 only depends on y5. Similarly, x3 only depends on y3. So there is this Markovian interdependence, and that's why this sort of model is very useful, because it will help you simplify things. Okay, I think we are now done with most of the stuff for today. I just wanted to mention also for your knowledge that the 2011 ACM Turing Award, which is like the Nobel Prize in computer science, it was given to the inventor of Bayesian networks. Okay, so Judah Pearl, 2011, this award was given for Bayesian networks, and that tells you the impact that this simple technique has created on the field of computer science. So with this, I will just try to conclude our lecture and give you a summary of what we have seen. So basically, we saw Bayesian networks as a set of or a graph of nodes and conditional probability distributions. So they are given by actually a set G and P, where this G is the graph, right? So you remember we had G equals to V and E, so nodes and edges, and this is the CPDs. So to know a Bayesian network fully, we need a graph which includes nodes and edges, and we need conditional probability distributions for all the nodes. Okay, now we also said one interpretation of a Bayesian network is as a generative model. So if you want to generate a variable, you want to generate an instance of something having certain characteristics, then Bayesian network can be useful because you can sample from them. Okay, so where variables are sampled, sampled in topological order. So you start off with the source node, you sample from it, and use that to sample the next variables in the chain or the graph according to the CPDs. Okay, then we saw the independence properties. So you can look at local and global independence properties which are identifiable via the D separation criteria. Okay, so and the last thing is about computing the probability any assignment is obtained by multiplying the CPDs. Okay, so we actually use Bayes' rule to compute conditional probabilities. And then marginalization is done to do the inference part. Again, marginalizing variables may not be easy. So hopefully next time we can look at a technique that can help you simplify that process. And doing that on paper is hard, but what I'm trying to explain is the general idea, and later computers can help you deal with all those numbers. So hopefully next homework we will have some exercise to see software tools that can do this. So you just need to specify the graph, the CPDs, and the probability numbers, and then you can make then you can make all sort of queries on that Bayesian network. So I guess that's what I had for today. And you will have your quiz number 5, I believe, for this week. And next week there will be homework. And also remember that next week you are required to submit your project mid-review report. So I'm not expecting anything formal. My assumption is that you've been working on your projects along the way, compiling information, organizing it, and preparing it in the form of a report. So whatever you have half-baked, unfinished, you can put it up for review. It helps you, it helps me to track your progress, and also I can give you feedback before you submit your final report. So it's a checkpoint. So try to take it seriously, and hopefully if you're on track, then things will be okay. Otherwise, you may have a problem when you, because oftentimes people are waiting till the last minute to work on their projects, and sometimes they end up doing extremely poorly. So this is to help you stay on track.
Sir, I have a quick question.
Yes.
For the essays, are we how much diagrams are we allowed to have? Because for my research paper, I have to include some diagrams to show visually like what I'm explaining. Like,
Yeah. So there's no limit. I think you can have as many as you think is required.
Okay.
But obviously everything has to be explained, so you need to have text as well.
Understood. Yes. Okay.
So
Thank you.
I mean, there's no format. I think everybody is doing a different project, so it depends on their specific topic.
Understood. I just want to know because we have a limit. Like we have to stay between 5 and 10 pages. So I was just wondering, like I have pictures, but I also have a lot of text to support it, and that's fine,
Yeah.
right?
Yeah, you
to
can
have
go
7
above the
pages.
limit is okay.
Okay. All right. Thank you.
Yeah.
Okay. And
Yeah.
what will you be looking for in these essays? Like, I'm explaining everything, so like I guess you'll explain to us in the midterm, like the next checkpoint, what you'll be looking for, grading for specifically.
In this midterm review,
Yeah,
there's
just
no
like no, also
there's no
like in the
grading.
final essay, like a rubric or something where we can follow and like make sure we get all
Yeah,
the points.
I think a standard IEEE format is a good guideline. So I need an abstract, I need an introduction, and then it comes to your specific topic, like what are the specific headings you need. Then I need results, I need conclusion. So
Got it. Understood.
so standard format.
Okay, thank you. Yeah.
Yeah. Okay, anything else? Okay, so I mean, if you have questions, you can send me emails for personal or individual concerns. And if not, then I think we are done for today, and we can meet next week.
Thank you, sir.
Okay.
Yeah. Thank you.
All right, then have a great evening.
Yeah.
Bye-bye.
Bye.
Bye. Thank you.
Mhm.